Okay, in our next example, we're going to be faced with a number of challenges unlike our first couple of examples, so you're going to want to pay close attention. Find the volume of revolution given the function y equals 2 minus x squared and the line y equals 1 about the line y equals 1. So I've gone ahead and I've made this sketch for you. The first thing we are focusing on is the function y equals 2 minus x squared, which I rewrote as y equals negative x squared plus 2. This is a parabola shifted up 2 units and turned upside down, and I've drawn that over here. And this region is also bounded by the line y equals 1, which I've drawn here, and it's also revolved around that line. Now I've also included for you the volume formula, but I've not added on to the end the dx or dy. Depending on the axis of rotation, it could be a dx or a dy, and we need to discuss when you use one or the other. So if your axis of revolution is horizontal, as it is here, then we're going to use a dx. If your axis of revolution is vertical, and we're going to see that in the next example, then it's going to be a dy problem. So our axis of revolution in this case is y equals 1, it's horizontal, so this is going to be a dx problem. And what that means is that our limits of integration are going to be a low x over here on the bottom and a high x for the upper limit. So that presents the first problem. Here is our low x over here, and here is our high x over here, but we don't know what those values are. So what I'm going to need to do is create a side problem in which the parabola is intersected with the line y equals 1. When does the parabola achieve a height of 1? So that's going to suggest the equation 2 minus x squared equals 1. This will result in x squared is equal to 1. And if I take the square root of that, I get x equals plus or minus 1. So this is negative 1 over here, and this is positive 1 over here. Now the other thing that's significant about the fact that we've classified this problem as a dx problem is that our radius ultimately will have to be described exclusively in terms of x. If this had been a dy problem, then all we should see here are y's, but since this is a dx, all we should see in here is x. Okay, so let's rewrite the volume formula and substitute in anything that we know. So we know that it's a dx problem because our axis of revolution is horizontal, and as a result, our low x is negative 1, our high x is 1, and now we have the challenge of figuring out how to describe the radius exclusively in terms of x. Now this is a little bit more challenging than the one we saw before. What I'm going to do is take my red pen and I'm going to place it on the x-axis, and I'm going to project a line straight up until I get to the farthest point of our region to be revolved. And I'm going to put a point there, and I'm going to call it xy. What that means is if we start at the origin and we want to get to that point, we're going to go over x and we're going to go up y, which means this whole length of the red segment is y units long. Now the radius of this region certainly isn't y units long, it's much shorter than that. We've got too much going on. In fact, this whole bottom portion of the red segment should be excluded because this shouldn't be part of the radius. So I'm going to make another line segment, this time in a different color. I'm going to use purple, and I'm going to put my purple pen on the x-axis, and this time I'm going to project up until I get to the closer of the two curves, which would be the line y equals 1. So the red line segment went to the far curve, and the purple segment went to the near curve, and the purple segment has a length of 1. So the radius of this blue region that's outlined in this bold blue is going to be not y, because y is too big. It's not going to be 1 because 1 isn't even inside of that region. But what it's going to be is the difference between y and 1. So I'm going to write y minus 1. Well, now we have the issue of the fact that the integrand is supposed to be exclusively in terms of x. So I'm going to have to do one more rewrite. Y is the same as 2 minus x squared, and then I'm going to subtract 1 from that, and then square it. Continuing to clean this up a little bit, We know that 2 minus 1 is 1, so we have 1 minus x squared, and then we'll FOIL that. So here's our setup for finding the volume of this region, and I'm going to leave the actual integration and evaluation of that integral to you. The answer is found on your worksheet, so go through the problem and check your answer to make sure that you've gotten it right. This problem definitely presented a few extra challenges which weren't in the first problem, and we're going to encounter these decisions that we have to make from here on out when we do problems like this. Let's go on to the next slide. So our last sample problem had a lot of new challenges presented in it, and now we're going to get a chance to really hone in on those new challenges and perfect them. In this question, it asks us to find the volume of revolution of the function y equals the square root of x, which is bounded by y equals 3 and x equals 0 about the y-axis. So this is our first problem in which our axis of revolution is the y-axis, or is a vertical axis. So I'm going to go ahead and highlight the fact that this is a vertical axis by making it blue like that. You can tell by this red arrow that we're going to be revolving around the x-axis. Let's start by writing the formula down, and this will help us get a sense of what we know and what we need to find. Now, we discussed in the last video that if your axis of rotation is vertical, then it's going to be a dy problem. And what that means is everything inside here, our radius, has to be expressed in terms of y. It also means that our limits of integration have to be in terms of y as well. So this is going to be our low y, and this is going to be our high y. So this is the function a wing, and we know that the wing starts at the origin, so this point over here is going to be 0. And we also know, because of the line y equals 3, that our high y is going to be 3. So we now know that this is going to be 0, and this is going to be 3. Now we need to figure out the radius. So I'm going to take my red pen out, and I'm going to place it on the axis of revolution, which is this time the y-axis. And I'm going to draw a line over to the curve that we're looking at. And I'm going to put a point here, xy. Now this red line represents the radius, and it has a length of x units. So the radius now is x, but we've got a problem because our function is given in terms of y. So this is yet another issue. But it's a pretty quick fix. If y is equal to the square root of x, if we were to square both sides, we get that y squared is equal to x. So it looks like, according to our diagram, our radius can be expressed as x, and x can be expressed as y squared. And if we put y squared here, then we have an expression for our radius which is expressed in terms of y. So our volume is going to end up being pi from 0 to 3 of y squared squared, which is y to the 4th, dy. So this is the setup. Again, I'd like students in my class to actually finish this problem out and check with the answer that I've provided on the worksheet before we go to our last problem. So in our fourth and final example, we're asked to find the volume of revolution using the curves y equals the square root of x, y equals 3, and x equals 0, this time about the line y equals 3. I've gone ahead and sketched those elements for you. Y equals root x, of course, is the wing, y equals 3 is that horizontal line on top, and x equals 0 is really just that little vertical piece on the left. Now we're revolving this solid over the line y equals 3. Y equals 3 is horizontal, and as a result, this is going to be a dx problem. Just like the x-axis is horizontal, this will be a dx problem. This also means that when I set up my limits of integration, I'm going to need a low x and a high x. Well, my low x is certainly going to be 0 because that's where this little region begins. But where this region ends is a little bit of a mystery. But I can figure this out by taking our function y equals square root of x and asking, when does this function reach a height of 3? So this becomes a little bit of a side problem. Our function is the square root of x, and I want to know when it reaches a height of 3. If I square both sides, I get x equals 9. So it really wasn't a big deal, but it required that I do this little side calculation. This is going to be helpful when I go to set up my volume formula, which I'm going to do now. So volume equals, of course there's a pi to begin. We've got our definite integral. The low limit is 0. Our upper limit is 9. We're going to make an expression for our radius, and then we're going to square it. And we also know that this is going to be a dx problem. And because it's a dx problem, that indicates to me that my expression for the radius has to be exclusively in terms of x. Now, to figure out our expression for the radius, I'm going to place my red pen on the x-axis, and I'm going to project a line straight up to the farthest curve of our region. That would be the line y equals 3. Now, this red line has a length of 3, but that certainly isn't the radius of this region. So I'm going to draw another line, this time in purple, again starting on the x-axis, and this time stopping when I get to the near curve. So the red line goes to the far curve, and that had a length of 3, and the purple line went to the near curve. And if I were to label this point right here as xy, that would tell me that this purple length is y. And of course, the red length is 3. So the red length is 3, the purple length is y. What do you think the expression for the radius would be? Is the radius 3? Is the radius y? Or is it something else? In this case, the radius of the solid that I'm showing you there, or the region that's going to form the solid, is going to be 3 minus y. Now our radius needs to be expressed exclusively in terms of x, so I've got to do another manipulation. We know from the original problem that y is defined to be the square root of x, so that's the substitution that I'm going to use. And I'm going to leave it up to you to square this out and actually do the integration to check your answer.